Okay, hello everybody, it's Cameron here, Mr. Hunter, with a little introduction to hybridization. It is really important. If it wasn't for hybridization, we couldn't effectively explain why carbon had 4 bonds. And if we can't explain why carbon doesn't have 4 bonds, we can't explain life, because life is carbon-based. You're all made of carbon. So let's have a look at that. And one of the interesting things that you should maybe ask yourself, I don't know if you ask yourself this, you probably don't wake up in the morning and say this, but why does carbon form 4 bonds? Well, the reason why it's a question that's worth discussing is if you draw out the electronic structure of carbon in terms of 1s2, 2s2, 2p2, you find, of course, that you have your 1s2 like this, and you got your 2s2 like this. Then you have your 2p2. Badly drawn, sorry about that. So this is 2p2, no it's not, it's 2s2. So this is 2s2. And this is your 2p2. Now, if you think about it, if you look at this in terms of covalent bonding, you could make a covalent bond here, or a covalent bond here. And then I guess you could say, right, well, you could have a dative bond here. Remember dative bonds? So you could have 1, 2, 3 bonds. Only 3 bonds. Now we know that carbon forms 4. So the reason why carbon forms 4 is pretty straightforward. We use a model called hybridization to explain the mixing of orbitals. In this mixing of orbitals, of particular energy and shape, remember the s orbitals are spherical and the p orbitals are dumbbells, px, py, pz, gives you a situation where you have not 3 orbitals of the same energy, but 4. Now these orbitals are slightly lower in energy than these two here. Slightly lower. I don't know if I've shown that effectively. Actually, I'm pretty sure I haven't. I'm going to erase that. Okay, they should be lower in energy. So, somewhere in between the p set and the s set, you have another new set. 1, 2, 3, 4. This electron here is promoted to here. And this one is now on its own. The energy to do this, because there always has to be an energy reason, is due to the drop of the p set. They drop in energy. Now there has to be an overall energetic reason for this. And it's probably because it allows carbon to form 4 bonds. And that's energetically favourable. It releases energy when it does it. So we've now got 1, 2, 3, 4 orbitals of the same energy. They're the same energy, and with the same energy they are known as degenerate. Degenerate means same energy. Okay? Now, these orbitals are not s or p orbitals, but they are taken from the combination of an s orbital and 3 p orbitals. They are mixed orbitals, so we call them sp3 hybrid orbitals. Hybridized orbitals. And these sp3 hybridized orbitals are not equidistant, but they're in between the energy of the S and P, and if you like, they're in between the shape of the S and P. So if this is the shape of the S, and these are the three P's, Px, badly drawn, sorry, three dumbbells lying along an axis, then the sp3 orbital looks a wee bit like this. A big lobe here, and a smaller one here. And this large lobe here allows greater electron overlap. And there's four of them, four sp3 hybridized orbitals. Okay, I could draw it, but I'd probably make a mess of it. So there's four of them that look like this. This is the sp3 hybridized orbital. And now that we have space, carbon has the possibility for 1, 2, 3, 4 covalent bonds. This is shown a bit better on this little diagram here. It's shown a lot better. That's why I put it in there. Here's your s orbital. 3p orbitals. Now what this diagram doesn't show is the energy situation. So for that you do have to look over there, because we are mixing these energies. That's very, very important. But it does show that you mix an s in 3p orbitals and you get 4 different sp3 orbitals. And they're represented as this set here. There's one of them here. There's a little node here. There's one of them here. There's a little node here. There's one of them here. And there's a little node there. And there's one of them here. Okay. Now you can see that this shape that this is going to form is going to be tetrahedral. But it hasn't actually made any bonds yet. These are atomic orbitals. They're atomic orbitals because they're in the atom, in the ground state. You've got your s and your p orbitals. 1s, 1s2, 2s2, 2p2 for hydrogen. These are what we would call simply atomic orbitals, and these are hybridized atomic orbitals. Now these are not the same as molecular orbitals. Don't worry about that diagram, I'm going to come back to that later. So we've now got the situation where carbon has got these 4 orbitals, sp3. So we can represent that like this. I'm not going to draw in the nodes, I don't want to confuse you. One here, one here, one here, and one here. And it's forming a tetrahedral shape. So along comes nitrogen. And hydrogen, and I'll give it a different colour for this. Hydrogen has a 1s shell only. It's not atomic number 1, it's 1s1. It only has an s shell. So the s shell overlaps with the sp3 hybridized orbital. And you have overlap of electrons here. One electron from, if you like, the hydrogen, and one from the carbon. And that same thing happens throughout the molecule. 1, 2, 3. So you have 4 situations where carbon overlaps with hydrogen in that way, and 4 situations where you have the sharing of covalent bonds. So you have 4 single covalent bonds. Now the single covalent bonds are formed by direct overlap of the orbitals. Direct overlap of the sp3 orbital and direct overlap of the s orbital from hydrogen. So if this is the sp3 orbital and this is the s orbital, and they just overlap directly. And this direct overlap is known as a sigma bond. And the sigma bond is what you have traditionally thought of as a covalent bond before. Head-to-head, direct overlap of atomic orbitals. Overlap of atomic orbitals. To give you a new molecular orbital called a sigma bond, or a sigma bond, which is a type of molecular orbital, we would call it. And this sigma bond is our old-fashioned covalent bond. Now, obviously, you can tell by the way I'm speaking that we are going to do something a little bit different. Before we do anything different, we actually just need to make sure that we are okay with the whole sigma bond thing. Carbon, hydrogen, hydrogen, hydrogen. These are all sigma bonds. The other type of bonding that we will discover is something called a pi bond. So, the shape that these make, well, this makes a tetrahedron. The bond angle is 109.5 degrees. Why would it do that? Well, all the electrons are in here, and the electrons are going to spread themselves out as much as possible because they don't like each other. The bond angles for all of them, it's a perfect tetrahedron, 109.5. And we say that the carbon atom to form this tetrahedral arrangement here is Sp3 hybridized. Okay, so that is your introduction to hybridization. That is an explanation of Sp3 hybridization. There are two other types that we'll study called Sp2 and Sp, and they involve pi bonds. That's this pi, not this pi. That's not a pi, that's like a C and D sign. I am so bad at drawing, but it's fun. Okay, bye. If you found this tricky, and it's a hard concept, review and rewind the tape, or the VCR. Rewind and replay and understand it again. Okay, that's all from me just now. Have a nice weekend. Bye.